Hi, I'm Amir Hossein Mirzabozorg, and in this video I wanna talk about Abaqus Simulation, Geomechanical Modeling of Fault Propagation Faults Part 1. Don't hesitate to ask any questions you might have about the explanations presented in this video using the comments below. We will try to answer all questions regarding the video details in the comments below. New Abaqus users who want to develop their modeling skills faster in their projects can request user-oriented online and offline services. Subsequently, we offer step-by-step guidance, tutoring, and consultancy. The online service includes online sessions, and the offline service includes creating special tutorials. In addition, a combination of the two can be requested. 50% discount codes are announced on our Abaqus Telegram channel and official LinkedIn page. Their links are provided in the description below the tutorial. Here we have the table of content of this tutorial. The interplay between faulting and folding mechanisms has been recognized in extensional and contractional settings. This tutorial explains how to create a 2D elastic plastic finite element model according to several reference papers investigating fault slip and uplift gradients, stress string patterns, and fault propagation faults structural evolution. Here we have the main reference paper for this tutorial, and here we have the other reference paper for this tutorial. Now I want to talk about mechanical behavior definition. Here we have table 1 of the main reference paper, and it includes material properties used in finite element models. And as the model includes 6 layers, here we have the mechanical properties of all 6 layers, including density, elastic properties, and plastic properties. So we must define 6 different materials and assign each of them to one of the layers. Now you can see the material definition of the first layer. Here we have its density according to the table 1 and also elastic properties, and finally the plastic behavior. And for all 6 layers we have used Mohr Coulomb plasticity, and it is widely used in the modeling of soil plasticity. And here I have defined friction angle, dilation angle, and cohesion yield stress. I go to Abaqus to show you the settings for the property module. I go to the property module. You can see 6 materials and, for example, the material for the first layer. In this analysis, the unit of length is meter. As mentioned before, the model consists of 6 layers from bottom to top. Layer 1, layer 2, layer 3, layer 4, layer 5, and layer 6. Also here we have the fault between layer 2 and layer 3. The fault has 45 degrees inclination and crosses the second and third layers. Its midpoint is on the boundary between the second and third layers. Several methods are available to model discontinuity in Abaqus. In this case, layer 2 and layer 3 are each divided into 2 parts. Layer 2 left, layer 2 right, layer 3 left, and layer 3 right. Here we have the modeling description written in the reference paper. If you read this section completely, you will understand that the solver and step are not mentioned directly. According to the time period equal to 10 seconds for the first and second steps, which are mentioned here, it can be guessed that the dynamic explicit step is used to analyze in a quasi-static manner. The problem is highly nonlinear due to all sources of nonlinearity, including plasticity, large deformation, and contact. So the dynamic explicit step is the best choice for solving it. Also, the time period of the third step is not mentioned here. Two different periods were used to do the simulations to study the effect of the period of the third step on the results. The values are 10 seconds and 100 seconds. Also, in this analysis, the elements will be dramatically deformed, and no solutions are suggested in the paper to avoid severe distortion of elements. As the dynamic explicit step is being used, the ALE can be added to the model to resolve elements' severe distortions. ALE means arbitrary Lagrangian Eulerian, and by adding ALE to the model during the simulation, the model will be remeshed several times, so the quality of the severe distorted elements will be increased during the simulation. Defining ALE in the models simulated via explicit solver is one of the common ways to avoid the errors due to severe distortions. In this paragraph of the main reference paper, the boundary conditions are explained. One of them is about defining fixed boundary condition for the top tip of the fault. It is mentioned here. This boundary condition is not generally physical, and why it should be implemented needs to be explained. It may help the fault maintain its shape so the other layers may slide more easily. Models are created with and without this boundary condition to study its effect on the result. Also, only the number of elements is mentioned in the reference paper. It is written here. The element sizes along the length and width of each layer are not mentioned. Hence, two different element sizes are used for the whole model to study the effect of the element size. Now I want to talk about studying different aspects of the modeling procedure. Here we have 5 models, and they are different in third step time period, global mesh size, ALE usage, and defining fixed BC on the top tip of the fault. For example, in the third model, the time period of the third step is 100 seconds and its global mesh size is 5 meters. Now I'm gonna talk about defining contact interactions. In this model, I have defined the contact interaction between layers by using surface-to-surface method. Here you can see all the defined contacts. When defining contact interaction via surface-to-surface method, contact interaction must be defined between surfaces that may be in contact due to further deformations beside the contact between surfaces that are in contact at the start of the analysis. For example, at the start of the analysis, according to the reference paper, we have contact between layer 1 and layer 2. And as the layer 2 is divided into 2 parts, then we have contact between layer 1 and the left part of layer 2, and we have contact between layer 1 and right part of layer 2. But for example, at the start of the analysis, we don't have contact between layer 2 left and layer 3 right. And in this case, During the third step, layer 2 goes on the layer 3 right, and it's because of the fault. Also, two contact interaction properties are defined according to the paper with friction coefficients equal to 0.01 and 0.25. The friction coefficient in the fault freak is 0.01 and in the layer freak it is 0.25. If the fault is not included in none of the contacting surfaces, then we will use layer freak, which is equal to 0.25. But if the fault is included in one of the contacting surfaces, then we will use fault freak, which is equal to 0.01. And because we want to have a sliding between the layers when we have fault. Now I want to talk about defining loads. Basically, we have both the force control and displacement control loads in this analysis. We have two force control loads, gravity and pressure on the top of the model. The gravity is defined in the first step and propagated in the next steps. And pressure is defined in the second step and propagated to the next step. And here we have the settings for the gravitational load, and we have applied it to the whole model. And as we want it to be applied in a quasi-static manner, I have defined a tabular amplitude for it, and it is 0 at the start of the step, and it is equal to 1 at the end of the step. And this column will be multiplied to this value, so during the first step it increases from 0 to 9.81 toward the negative y direction. Also, this value is equal to the time period of the first step, which is 10. Now I want to talk about defining boundary conditions. I have defined all these boundary conditions according to the main reference paper. And here we have the displacement control loading, which is applied in the third step. And as it must be applied in a quasi-static manner, so I have also defined an amplitude for it. Its type is tabular, and we have these settings for it. Here it is similar to the amplitude defined for the gravity and pressure. If I go back to the previous slides, here you can see that for the third step, its time period is 100. So when we are modeling the third step, here we must write 100 instead of 10. And about the mesh generation, for all the layers, I have set the approximate global size equal to 10. And in none of the models, the seed edges or local seeds tool is not used at all. And in only one of the models, the element size is set to 5 instead of 10. If I go to the previous slides, in the third model, I have set the global mesh size equal to 5 meters. So I must write 5 for the third model. And about the element type settings, I have set the element library to explicit, the family to plane strain, and geometric order to linear. So the element name will be CPE4R. Basically, there are no quadratic quadrilateral elements in the element library of the explicit solver. So the only choice is the linear order when we want to use explicit solver and we have the quadrilateral elements. In the previous slides, I talked about a boundary condition that is not physical and it must be applied on the top left corner of the layer 3 right. Here its name is BC new and it is defined in the third step with these settings, and it is applied here. As you can see, here we have layer 4, here we have layer 3 left, and here we have layer 3 right. And this boundary condition must be defined at the top left corner of the part named layer 3 right. It must not include any points of the adjacent parts because it will prevent the sliding and folding of those layers. Now I want to discuss the results. I go to Abaqus. Before going to the visualization module, I want to show you some of the settings. As you can see, we have 5 models, and for example, in model 2, we have 3 steps like the other models, and these are their settings. The second step, as you can see, I have not defined mass scaling for all the steps and for all the models. And here we have all the defined contacts, and for example, the contact between layer 1 and layer 2 left. It is like this. And we have these interaction properties. And then I go to the load module. We have gravity and pressure. Its definition is according to the main reference paper, and I don't define any predefined fields. Also, we have these boundary conditions. Here we have the displacement control loading, and also this is the mesh. As you can see, here we have this number of elements, and also we have this kind of element in the model. The number of elements used here is much more than the number of elements used in the reference paper. Even in the third model, as you can see, we have used much more elements. And here we have these simulations. I go to the visualization module. I want to have job 2, job 3, job 4, job 5, and job 8. And for example, job 2, which is for model 2. We have the first step and then second step, and then as you can see in the third step, these 5 layers are moving. And here we have a sliding on the fault. And as you can see, here we have severe distortion of elements. It's because we have not used ALE in model 2. Then we have model 2 ALE. The difference between model 2 and model 2 ALE is the usage of ALE. Here you can see that there are no severe distortions. Okay, and if I set it to PE, there are no severe distortions. And then the third model. In the third model, also ALE is used, and the global mesh size is 5, and its time period is 100. Its result is job 8. That's it. If I hide the mesh, it's better for illustration. We have the first step, then second step, then third step. And as you can see, at the end of this job, we have severe distortion of the elements. But until 87% of the simulation, it has been done. And here we have PE values. The results of this analysis is more reasonable and more close to the reality. Also, we have job 4. The model of job 4 is model 2BC. In model 2BC, we have not used ALE, and also the non-physical boundary condition is used. As we have applied the non-physical BC, then this point will not move. I mean the point of the layer 3 right. If you see, it is not moving. And we have this kind of deformation. And finally, job 5. The model of job 5 is model 2 ALE-BC. And in model 2 ALE-BC, both the ALE and the non-physical boundary condition are defined, and as you can see, only 36% of the simulation is done. If I show you the third step, and then we have error. Now I want to talk about purchase of the complete package. The complete package of this tutorial includes CAE, JNL, INP and ODB files and reference articles, step-by-step tutorials about creating the models including detailed explanations, and the package specifications and payment details are provided in the video description below the video. 50% discount codes are announced on our Abaqus Telegram channel and official LinkedIn page. Their links are provided in the description below the tutorial. What you will earn from the step-by-step videos included in the premium package of this tutorial. How to do all the steps one by one to set up the FE model. How to define ALE with appropriate settings to avoid severe distortion of elements and subsequent errors. How to define boundary conditions correctly. And finally, how to define contact interactions to include all the possible contact interactions and avoid pre-processing errors. You can contact us via Telegram or WhatsApp, and you can send email to us. About our services, we have one-on-one tutoring, and we can make special tutorials to your order, and we can conduct high-quality simulations for your thesis exercises and industrial projects, and we have training sessions, courses, webinars based on the user requirements, and we offer support in writing the modeling and result discussion part of your thesis, and we have consulting services for MSc, PhD positions or job interviews, and we can help you to prepare the presentation of your simulation works. Now I want to suggest you several related videos of our YouTube channel. Thank you so much for watching this video. Have a good time. Goodbye.